Welcome to Science Makes Me Smile. Every idea begins as a question, not to settle the truth, but to explore it. What we discover along the way depends on how deeply we're willing to think. I'm young Dr. JGC. Let's begin.
The question no one asked. For many years, I had the quiet joy of teaching basic chemistry as part of an anatomy and physiology class. Most of my students were future nurses. I have always been a big fan of pure science. I take great joy talking about atoms, ions, chemical bonds, perhaps even more than the long bones of the body. And so, year after year, I stood before them and described the atom in its simplest form. As I spoke, I would turn to the board and begin to draw. First, a small circle in the center. This, I would say, tapping the chalk lightly, is the nucleus. Then around it, I would sketch a larger circle, sometimes several, to place the electrons. Little circle with plus signs inside the center for protons. Little circles with no signs beside them for neutrons. Tiny circles with minus signs orbiting outside for electrons. At the center, I would explain, is the nucleus. Tiny, dense, and powerful. Inside it live protons and neutrons. Around it move the electrons, almost like a restless cloud. Protons are positive, neutrons have no charge, electrons are negative. The diagram was simple, the explanation was clean, it made sense. And thankfully, no one ever asked the question that lingered quietly in the back of my own mind. If protons are positively charged, why don't they repel each other and fly apart? After all, we teach very early that like charges repel, two positive charges push away from one another. That is not advanced chemistry, that is foundational. So how can several positively charged protons sit side by side inside a space unimaginably small and not explode away from each other? If a student had raised a hand and asked, I suspect I might have hesitated. Perhaps I would have said something like, well, maybe the negatively charged electrons surrounding the nucleus help balance things out. Or perhaps, if I were being honest, that's a very good question. I'm not sure. At the time, such an answer might have been enough for an introductory class. But now, with deeper understanding, I know that explanation would not have been correct. The electrons have almost nothing to do with it. The nucleus is about 100,000 times smaller than the entire atom. The electrons live far away compared to nuclear distances. They cannot reach in and hold protons together. They cannot counteract the immense electric repulsion inside the nucleus. Something else is at work. If you ever had the same issue I had with this concept, you are about to understand why the positively charged protons do not repel each other inside the nucleus of an atom. Deep within the nucleus exists a force far stronger than electrical repulsion. It is called the strong nuclear force. Unlike electric force, it does not depend on charge. It acts between protons and neutrons alike, and at extremely short distances, when particles are almost touching, it is extraordinarily powerful. The protons do repel each other. That part is true. But when they are close enough, the strong nuclear force overwhelms that repulsion and binds them together. It is as if nature built a glue stronger than electricity, but one that only works at incredibly small distances. Neutrons play a quiet but crucial role in this story. They do not add electrical repulsion, yet they participate fully in the strong force. They help stabilize the nucleus without increasing the push outward. That is why heavier elements require more neutrons than protons to remain stable. Looking back, I realized that what I taught was not wrong. It was simply incomplete. At the level of nursing chemistry, the simplified model serves its purpose. Students learn about ions, chemical bonds, pH, and biological molecules. They do not need to dive into nuclear forces, but the deeper truth is even more beautiful. The nucleus should not hold together. By electric logic alone, it should fall apart. And yet it does not. Because hidden within matter is a force strong enough to bind the very heart of the atom. If that force were slightly weaker, atoms would not exist. If it were slightly stronger, matter as we know it would be entirely different. Every molecule, every living cell, every human being depends on this delicate balance. Perhaps I should have hoped that one curious student would ask the question I silently carried for years. Why doesn't the nucleus explode? Today I would smile, not with hesitation, but with gratitude, and say, that question takes us beyond chemistry. It takes us to the forces that hold the universe together. And the lesson would become even more beautiful than the diagram on the board.
Every conversation leaves a trace, not of certainty, but of insight. What you do with it is up to you. I'm young Dr. JGC. Until next time. Comments, questions, suggestions are welcome. Please remember to like and subscribe. Science makes me smile.
Hit subscribe below so you never miss any of our new episodes.